Hello, thank you for watching this video. So on this video, we'll be doing question 7 of November 2021 question paper physical science paper 1. And these are electrostatics. So I'll read question 7 statement and then answer the questions that follow. So let's go. They are saying a small neutral sphere acquires a charge of minus 1.95 times 10 to the power minus 6 coulombs. So you had a sphere which was neutral, right? And then this sphere of yours acquired a charge of what? Of minus 1.95 times 10 to the power minus 6 coulombs. So that's what they are telling you. So 7.1.1, they are asking, were the electrons added to or removed from the sphere? So they are asking for the sphere to move from being neutral to acquire that charge, were electrons removed or added? So they are saying choose added to or removed from. So the electrons were added to the sphere. The electrons were added to the sphere. That's what happens. So if you have a sphere like this, and then this sphere maybe becomes in contact with a negatively charged object, then electrons may be transferred from that negatively charged sphere into this neutral sphere, or maybe from that negatively charged object into our neutral sphere. So electrons may be transferred by contact. That's what possibly happened to the sphere, or maybe by touching, to be more exact. So that's what might have happened to the sphere. It was in contact or with another charged object, or it was touching with another charged object, and it acquired that electrons, that charge, which was as a result of transfer of electrons. Right? So they are saying now 7.1.2. They are saying 7.1.2. Calculate the number of electrons which were added or removed. So they want us to calculate the electrons that were added, because we know that they were added. So you know that your number of electrons is equal to what? It's equal to your charge over your electron charge, which is the charge, the current charge of your sphere divided by electron charge. So what is the current charge of the sphere? It's minus 1.95 times 10 to the minus 6 coulombs divided by the electron charge, which is minus 6, 1.6 times 10 to the power minus 19 coulombs. So it's coulombs, they cancel each other out. Therefore, your number of electrons is equal to the answer to that. So, which I'm going to punch now and see what we get. You say now minus 1.95 times 10 to the power minus 6 all over minus 1.6 times 10 to the power minus 19 coulombs. So we are getting that the number of electrons is 1.22 times 10 to the power 13 electrons. So this is the number of electrons that were added to your sphere. Now, move to the next one, which is 7.1.3. So, what are they saying in 7.1.3? They are saying, define the term electric field at a point. So they want you to define the term electric field at a point. So, if you have a charged object, let's take that charged sphere there. You have a sphere here. It's negatively charged, right? When you have a charged object, it can be positive or negative, right? It generates a field around itself. So you will have a field around this object here, around the sphere of yours, in all directions, right? So here's a sphere. So this is the electric field around our object, which is what we're trying to define. Okay, this doesn't look very nice. I'll try to fix it. Take one line and put it maybe here. Take the other, put somewhere there. I think it looks better now. So you have a negatively charged sphere. It doesn't have, it can be positive, depending on what example you want to do. I'm just using this as an example just to explain what I'm trying to say. So if you have a charged object, it generates a field around it, an electric field around itself. So which is what we're trying to define, right? So now, so if within this field close enough, you put maybe a positive charge here. This positive charge here will interact with this charge of yours. Actually, this charge of yours also have its own field around itself, right? Its field will interact with this one. It will interact with the field of, with this negative, with this charge, with this field of this L. So this positive charge of yours that you place here have its own electric field around itself. Because I said any charged object will have an electric field around itself, which is what we're trying to define. So this electric field will interact with that of the negative charged object, right? There will be an interaction between the field and the field of this negatively charged sphere here. There will be that interaction. That interaction will be in the form of force, right? So to define the electric field, it is the electrostatic force experienced per unit charge of this charge here. Which means it is not a force, electric field is not a force, right? But it is the measure of how much force per coulomb of this charge that I've placed here, which is how much electrostatic force experienced by each coulomb of charge that is placed here. Which means how much newtons per coulomb experienced by this charge that I've placed here in this electric field. That is how you define an electric field, maybe. So you define it by saying it's the electrostatic force experienced per unit charge at that point, which means you want to know how much newtons of force are experienced per coulomb at that point. So let's write it down. So we'll say electric field is the electrostatic force experienced per unit charge at that point of interest. So electric field, it is the electrostatic force experienced per unit charge at that point, which is, it is the magnitude of newtons per second, number of newtons per coulomb experienced at that point. That's what an electric field, it is not a force. It's a force per unit charge. Done. Go to the next one, which is 7.1.4. So that's saying calculate the magnitude of the electric field at a point that is 0.5 meters from the center of the charged sphere. So they want us to find the magnitude of the electric field. So your electric field, just define it as the electrostatic force per unit charge, right? So which is also equal to this over R all squared. So your electric field will be equal to what? Your electric field will be equal to K, which is 9 times 10. There's 9 times your charge. What is your charge? It's 1.95 times 10 to the power minus 6 divided by the distance, which is 0.5 meters squared. Right? So your electric field is equal to the answer to this. So let's patch that and see what we get. So say 9 times 10 to the 9 times 1.95 times 10 to the power minus 6 divided by 0.5 all squared. So it comes up to be 70,200 newtons per coulomb, right? So which means it's 0.5 meters away from our charge, right? A charge that is placed there will experience a force of 70,200 newtons for each coulomb that it contains, or for each coulomb that it carries. So that's what an electric field is. So it's not a force, it's a measure of force experienced by each unit charge, by each coulomb. So we move to 7.2. Looks like we will have to have a drawing. So let me draw this, then we will continue. So now we're doing 7.2. 7.2. Two charges Q1 and Q2 are fixed 0.02 meters apart. The magnitude of Q1 and Q2 is the same, and Q1 is negatively charged. The small charged sphere with a charge of minus 1.95 times 10 to the minus 6 coulomb is placed at point P, which is 0.03 meters east of charge Q, as shown in the diagram below. The sphere at point P experiences the net electrostatic force of 1.38 newtons west. Let me try to read this thing again. They are saying 2-point charges Q1 and Q2 are fixed 0.02 meters apart. The magnitude of charges Q1 and Q2 is the same, and Q1 is negatively charged. The small charged sphere with a negative charge of minus 1.95 times 10 to the minus 6 coulomb is placed at point P, which is 0.03 meters east of Q2. That's as shown in the diagram. The sphere at point P experiences the net electrostatic force of 1.38 newtons west. So we have this equation here. We have the sphere Q1 and Q2, which have equal sizes, right? But this one is negatively charged. No problem. So they're saying now our sphere from above, which is this one here, is placed where? Is placed at 0.03 meters east of Q2. And we're told that it experiences the net electrostatic force of 1.38 newtons. No problem. They're saying now, calculate the magnitude of the charge on Q2. They want us to find the magnitude of the charge on Q2. They want us to find this charge here. No problem. So, we're told that the net electrostatic force here at point P, which is at this charge that is here, is 1.38 newtons westwards. No problem. So what do we do? I'll take my west as negative, I'll take my east as positive. So which means the net electrostatic force is negative. Right? No problem. So we know the sphere is negative or given. And we're told also that sphere Q1 is negative. These two have the same sign except this one is negative. So our friend here is positive. Right? Also, another reason that you can use, you can say, okay, if the net electrostatic force of this one is this side, actually, let me draw the free body diagram. So if you are this sphere here, right, which is sphere P, let's draw its manifold diagram. It experiences a force to that side. So this is the force of Q1 on our sphere, right? On our sphere, what do I write it? Let me just write our sphere as P. So it will experience this force, the force to the left. But we know that the net electrostatic force is to the west, which means this one has to be positive, so that it attracts this one. It attracts P. Because we know that the net electrostatic force at P, we know that the net electrostatic force at P is westwards, which means between these two, one of them should be attracting P, so that it moves westwards. But we know for sure that it's not Q1, because Q1 is negatively charged, we're told, right? So as a result of Q1, P will experience a force that pushes it to that side, right? So I will say P now is feeling the force of attraction because of this one. So this is the force of Q2 on P. So our net electrostatic force at P is a result of these two forces. Of course, if these forces are on the ground, you can say, okay, you have your force of gravity and maybe your normal force if they are placed on the ground. So now our net force here at point P, our F net, is a result of what? Of a positive, this force, which is Q1 at P, plus a negative, that one, which is negative force of Q2 at P, right? And I would think this one is a stronger force, because this one is moving to that side, so this one is the more dominating force, this one than this one. So what do we do? So okay, our net force is equal to, this is the electrostatic force, which is K, Q1, the charge of the sphere, over the distance, the square of the distance between them, minus K, Q2, the charge of the sphere, over the square of the distance between them. Right? Now we're left to substitute. What were we told? We were told that the Q1 is equal to Q2, right? So we can substitute the same thing there, because these two we're told that they are equal, Q1 and Q2. We're told that they are equal, Q1 and Q2. So our F net is what? Is minus 1.38. I'm saying it's negative because I decided that everything to the west is negative, and we know that our net force is negative, so it is to the west. Which is K, what is K? 9 times 10 to the power 9 times Q1, right? Because we want the magnitude of Q2, which is the same anyway. So I'll put Q2 times charge at S, which is, what is it? Charge at S is 1.95, right? Times 10 to the power minus 6, all over the distance between Q1 and QS. Where is Q1? Q1 is this one, and that one is there. So the distance between them is this and that. So the distance is 0.02 plus 0.03, all squared, minus, what is it? So it's going to be Q2 again. Actually, it's going to be K, which is 9 times 10 to the 9, times Q2, which is this, times that, which is 1.95 times 10 to the minus 6. So this is the same as this. all divided by what? The square of the distance between Q2 and QS. Q2 and QS, the distance is only 0.03 meters all squared. So now what we're left to do is to punch this. So actually, let me just try to rewrite it because it doesn't look very nice. So we have minus 1.38 is equal to 9 times 10 to the power 9 times 1.95 times 10 to the power minus 6 Q2, all divided by 0.05 all squared minus 9 times 10 to the power 9 times 1.95 times 10 to the power minus 6 times Q2, all divided by 0.03 all squared. Then go down. So we have minus 1.38 is equal to, punch this and see what you get. So we say 9 times 10 to the power minus 6 times 1.95 times 9 times 10 to the power 9 times 1.95 times 10 to the power minus 6, all divided by 0.05 all squared. Actually, we had the answer to this one. So this is what we have here is 7.02 times 10 to the power 6 Q2 minus the answer to that, which is 1.95 times 10 to the power 7 Q2. These are like terms, therefore minus 1.38 is equal to, find the difference between the two, 7.02 times 10 to the power minus 6 minus answer. So we get is minus 1.25 times 10 to the power 7 Q2. Then divide by negative 1.25 times 10 to the power 7 both sides. So you get that the Q2 is equal to minus 1.38 divided by a thing, which is 1.11 times 10 to the power minus 7 coulombs. So this is the magnitude of charge number 2. So we're done here, and we hope that it is correct. And of course, we hope it does make sense to you as it does to us. Thank you for watching. Cheers.